Welcome, Mindsetters, to this session of Grade 10 Maths live on Learn Extra. Hope you guys are ready. You got your pens and pads out and you guys have made some notes. I've got Jacques here who's going to be taking the session today. So, Jacques, what are we going to be doing today?
So we're looking at some serious analytical geometry for grade 10. We're going to look at the formulas, the way the formulas are constructed, and once we've done all the theory, we're going to do 2 or 3 problems. So it's going to be a nice session, folks. Don't run away because the work is not difficult. It's actually easy. And once you understand how the formula works, you won't forget it.
All right. Okay, thank you, Jacques. So while Jacques makes his way to the board, I'm going to tell you, Mindsetters, I know last week was winter school and there was a whole lot of different things, crazy things. Right now, we're back to normal. I have this Casio calculator that I'm giving away and this labeler. So Mindsetters, you know the drill. Get on the page, chat to me, talk to me. The best post wins the calculator and the labeler. And on that quick note, just for the Saturday winter school, I want to say congratulations to Kay Harpishad, who SMS'd us for the grade 10 math session. Congratulations, you get that prize sent to you, and I hope you have fun with it. But Mindsetters, I hope you guys are ready. You've got your pens and pads out, as I always say, and you guys are ready to make notes, because there's a long session ahead of us, so make sure you are ready. But right now, I'm going to keep quiet now, watch the page, and I'm going to hand it over to Jacques. Jacques, take it away.
Thanks, Ty. Okay, folks, let's have a look at how these formulas work that you're supposed to know. Remember, a formula sheet is at the end of your paper, but that formula sheet is only there for you to remind yourself that a plus is a plus and a minus is a minus. It's not for you to go and look for a formula and try and fit it into the work that you're doing. Okay, we've got a straight line. We've got a line segment AB given to us, and we're looking at, first of all, to measure how long this line is. Okay, now let's see how this works, folks. We've got a point A, and I always like to label my coordinates, the x coordinate of A, and then the y coordinate of A. That way, whoever looks at my work knows exactly which point I'm busy working with. Now, the same goes for x of B and y of B. Okay, those are the 2 coordinate pairs that we are given. We asked to find the distance between those 2 points or the length of the line AB. Now remember, you might need lengths if you think about geometry. It's called analytical geometry. You might need lengths to refer to isosceles triangles or to prove that a figure is a square because opposite sides are equal. Equilateral triangles, everywhere where you work with length in geometry, and you have coordinates, this is where this rule is going to apply. Now let's see how they derived it. If I do a little bit of a construction here, let me just choose another color. From that point B, I'm going to drop a perpendicular. And then from A, I'm dropping a line that runs parallel to the x-axis. Folks, where these 2 cut each other is the point C. Now that C has a particular relationship with the coordinates A and B. Because this line is parallel, folks, the y values on this line, everywhere on the line will be shared with one another. Now, what is this thing doing to me? This y value here and the y value over there and the y value over there is all going to equal the y value of point A. Okay, so immediately we can say that this will be a shared point, the y coordinate of point A. Now, if I look at the x coordinates here, the line BC, folks, remember this is perpendicular. All horizontals and verticals are always perpendicular to each other. So the line BC is a vertical line, meaning that all the x values on that line is shared with the x value of point B. So the x value of point C is the same as the x value of the point B at the top. Okay, now it's time for us to talk about the length. Now, before I do that, let's just talk about vertical lengths and horizontal lengths. If this is at the y value of 7, folks, and my other hand is at a y value of 5, what do I usually then do to find the length of that line? Yes, you're right. We take the top y value minus the bottom y value. Now the same for the x values. If the x value over there is 10 and this x value is 5, we say it's the larger x value minus the smaller x value, which gives us the distance or the length of the horizontal line. So to find the length of BC, all I need to do is take the top y value and I minus it with a y value of the point at the bottom, which is the point C. The same for the x values. To find this horizontal distance, I take the furthest x value, which is x of b, minus the x value that's smaller over here, the x value at point A. Okay, that's quite exciting. Now you see a triangle in which I have a 90-degree angle. I have a right-angled triangle. And you know from your baby mathematics that if I work in a triangle that looks like this, I can apply Pythagoras. And that's exactly what they did. They said, okay, the length of the line AB, okay, so AB is nothing other than the square root of the length BC squared plus AC squared. And now we've got the length of BC and AC. I'm going to say it again. The length of the line AB by Pythagoras is the length of this side squared, AC squared, plus the length of BC squared, that vertical length. So immediately I've got those lengths, I'm going to put them in. The horizontal length for AC is XB minus XA all squared. And what do? I add it to YB minus YA all squared. Okay, folks, and that's all I need to do. Comes from good old Pythagoras, solid mathematics. If I want to find the distance between the 2 points, I apply Pythagoras. Now, you're not going to go through this proof every time you find this problem in a question or a problem that you're doing, the idea of length. Let's see how the final version fits in with the diagram that's on the screen, folks. XB minus XA. I'm looking for the length of AB. So it's the x value at B minus the x value at A, all squared, plus the y value at B minus the y value at A, all squared. So you just need the coordinates of those 2 points to find the distance between them. If it's point P and Q, you'll say the x value of P, I beg your pardon, minus the x value of Q all squared, plus the y value of P minus the y value of Q all squared. And that gives you the length of the line segment, PQ. Okay, let's see our next formula that we are going to look at. Our next formula deals with the issue of halving that line segment. Now, if I go back, let me just go back to our previous diagram. If I look at this diagram and I want to find the midpoint of this line, look at that. This little bit here is equal to that little bit there. So let's call that the point D. Okay, folks, now again, it's a play on coordinates. I can do one of 2 things. I can say to myself, okay, I've got 10 here. Let's talk about a horizontal length. I've got 10 here, and I've got 6 over there. The distance between 10 and 6 is 4. So if I want to go halfway, I must halve that distance. Now, half of a 4 is 2. So I go to the bottom limit, which is 6, and I add 2 to get to 8. And if you go from 8 to 10, you add 2 as well. The alternative is a quicker one. If I take the 6 and I take the 10 and I add the 2 together, I get 16. And if I half that 16, I end up at the midpoint, which is 8. So it's putting them back to back and then halving the distance would give you the midpoint of that line segment. Okay, so let's see how that's going to work. If this was a 10, let's just write down what we just said. If, let's say for argument's sake, that was 10 and this was 6. We know the distance between the 2 is 4. So if I half that distance, I go to the midpoint between the 2 points, which leaves me exactly 2 units away from 6, which gives me 8. Okay, that's my midpoint. Alternatively, I can say, okay, let me take the 10, and let me take the 6, and let me add the 2. Then I get 16. If I half that 16, I end up with 8. Now that's equivalent to taking the line of 6, taking the line of 10, and halving in between the 2 there. That's what I do if I add the 2 endpoints. And that's exactly what I'm going to do to find the midpoint. The midpoint, MDP, I always use that abbreviation. The midpoint of a line segment. Let's go to the next diagram. Over here, let's say this is point A, and this is point B. And remember, folks, it's based on that same construction. So if I have my midpoint over here, which means those two lines are equal to one another, I can draw in my horizontal and my vertical, and then remember they're perpendicular. From this line, or from this midpoint, if I draw a line that runs, let me just get rid of that, parallel and goes through that point, that line here will be parallel to the vertical over there. So what it will do on this point over here, at that point there, it would halve the horizontal line as well. Okay, so if I want to now go and find the coordinates of that point, I need to take my two extreme points, let's call that C, and let's still stick to D over here. The x value of point D, which is my midpoint, will be the addition of my two extreme points, the x of C, plus the x of A, divided by 2. And that takes me straight into that midpoint for the x-coordinate. The same happens for the y-coordinate. If I come in with a horizontal line over here that goes through that point, it will run parallel to the x-axis, and indeed it would halve that side as well. So if I want to find the midpoint of that side, it's going to be the same as the midpoint of D, because it runs along the parallel line. Okay, so how do I find that midpoint? We said we take the two extremities. So the y-coordinate of point D, which is the same as the y-coordinate of that point over here, it's the sum of the two, the y-coordinate of B plus the y-coordinate of C, that is halved. Okay, folks, so far we've seen the distance between the 2 points comes from Pythagoras' theorem. And then how do I find the midpoint of that line segment? I just need to remember what I did when I look at the midpoint of the line. Now remember, there's one of two ways to do this. Whichever way you're going to go, you're going to end up with exactly the same formula than what I have over here. Okay, folks, let me just check here. I wrote XA and XC. It's actually YA. No, it's YA. We're working with this line's midpoint. So I said it's YB plus YC that halves it and gets us to this point over here. So it's the extreme points that we add and we halve. And for this horizontal distance, the point over here will be the same as what the point coordinate will be over there. How did I get that? I add the two and I halve them. Okay, let's look at my last formula that I want to discuss with you before we're going to do some problems. That's the point A over here again, and the point B over here. Now, you should be familiar with this formula. If you're not, let's have a look and let's see where it comes from. If we talk about the gradient of a line segment AB, we're talking about the slope of the line. At what angle, and sometimes we're going to talk about the angle, at what angle does this line lie? We call that the gradient of the line AB. So if I want the gradient of the line AB, I need to know how are the x, as the x values are changing, how are the y values changing? They change in a particular relationship with one another. And that relationship is what we call the slope of the line. Okay, so folks, we're again referring back to our horizontal and our vertical lines. And they're still perpendicular to each other. If I want the gradient of this line, I want to know what's the relationship between the changes in the x values and the changes in the y values. That gives me my gradient. So it is the change in the y value divided by the change in the x value. And another word for gradient is slope. Okay, so at what slope is this line that's lying on at that point? At what slope is it lying at? Okay, so if I want to find that slope, remember, where is your change in y value? Your change in y values lie vertically over there. Your change in x values lies horizontally over here. So if you want to find the slope of this line, the line segment, the particular line segment AB, you need to find out at what rate is this changing in relation to the rate at which it changes. That is a rate. So that change divided by this change gives us the rate delta y, delta x. Change in x, change in y over change in x. If I look at this now and I use my two extreme points, I can find that by saying it's the y value of b minus the y value of a will tell me what vertical distance did I change. Now, what is that based on, folks? If this is a 7 and this is a 3 down here in terms of its y values, I would again say the difference between those two lines, remembering that they run parallel, gives me the change in y. So 7 minus 3 gives me the 4. The same way as the y-coordinate of b minus the y-coordinate of a will tell me the distance between those two parallel lines. Now the same happens with the change in x. I'm wanting to know from this point to this point, how far are their x values apart? Okay, it comes down again. If that is 10 and we have a 6 here, it would be the difference between those two. Now remember, why is it the same? Because the line is vertical. Okay, this line is a vertical line, therefore it shares its x values. So this will be the same as the x of b and the x of a. Okay, that's quite a mouthful to try and show you where these rules come from. Okay, but you don't need to know the whole process from now onwards. If you see me asking you what's the gradient of the line, you know you've got to work out the change in their y values of the two extreme points, the change in the y values, then divide that by the change in the x values. Once you've got that, you've got your gradient of your line. Now, folks, the next focus in analytical geometry is exactly the straight line and how to find the equation of a straight line, etc., etc. All of that is based on this idea of the gradient of a line. Now, you've got to remember one thing. You've got to remember that if you work with a particular line, you need to know 2 points on that line. That makes the line segment unique. I can, through that point, draw quite a few different lines, and they will all go through the point, but they won't have the same slope. But there's one and only one line that I can draw that will go between those 2 points, and that is that particular line. That is why this idea of the gradient is going to become very important in your life. And when you get to matric, there's a whole section called differential calculus, which is based on this idea. Okay, I think that's enough theory for now. Ty, is there anything online happening there that somebody wants to talk about?
So far, not really, besides everyone's just having fun in the show.
Oh, excellent.
And they're just glad we're back.
Good.
So I think we're going to take an ad break now, and yeah, I think so. Mindsetters, make sure you get on the page and keep chatting to me, and remember to keep posting. The more you post, the higher your chances of you getting this Casio calculator or this Casio awesome labeler. So make sure you guys get those posts in. But for now, we're going to see you after this break. Welcome back, Mindsetters. I hope you had a nice little break. You went and did whatever you had to do. You went to the bathroom, you got some water, some snacks, whatever you needed to do so you do not have to fidget or go anywhere, because you guys need to pay attention. And I just want to send a quick shout out to actually one of the viewers, Stephen Nkahamang. I'm sorry if I butchered your name. I'm so sorry. He says, "Hi guys, it's Stephen from Malawi. Your show and channel make us good mathematicians. Much love." We want to say much love to you. Thank you for tuning in, because you know what? We do these shows because of you guys. So Mindsetters, I hope you guys are now ready for this session, because I'm about to hand over to Jacques, who's going to continue. Jacques, are we good to go?
Excellent. Great
All
stuff.
right. Jacques,
Thanks, Ty.
take it away then.
Okay, folks, I told you the gradient's going to be a very important concept in your life. So let's just look at a few principles that you continuously need to remind yourself of when you look at a line segment and its gradient. Here we have a line that slopes in that direction. Okay, so the direction of this line goes increasing. We talk about this as an increasing line. When you talk about the function, it's an increasing function in mathematics. Okay, if a function increases, the gradient of that line is positive if the line slopes in that direction. If it slopes in another direction, in other words, decreasing, the gradient of that line segment AB will be a negative line. If the gradient is negative, the line is decreasing. All that means, folks, let's look at the line AB that's on here, that's actually an increasing function. The bigger the x's become, the bigger the y values become. Then it's an increasing function. The opposite is true about the second line. As the x increase, the y values are decreasing. Now, the way I always remembered this at school, that the gradient is negative if the line slopes in that direction, is by thinking of a capital N. Look at that. There's your line, and it's sloping in that direction. Hence, the gradient is negative. Okay, now let's ask ourselves, where is a gradient equal to 0? And that will happen if there's no change in y values. So in other words, the line is horizontal. Now, sometimes in analytical geometry, folks, you get those lines. You need to be very awake if you look at the coordinate pairs that they give you in analytical geometry. Because if there's no change in the y values of two coordinates, it means the line is a horizontal line that connects those 2 points. Now, in the same way, so this line will be, let me draw it in there, will be a horizontal line. We also get a gradient that rarely pops its head out. And that's a gradient that is undefined. And we usually see on our calculator an error symbol, or on a graph, it is a line that lies vertical. In other words, the change in the x values are 0. There's no change in the x values. Hence, the line is going to be a vertical line. Okay, so if the delta x's are naught, those lines do exist, even though the gradient doesn't. Okay, those lines are vertical. What do I need to look for? I need to look for x coordinates that are the same. Okay, then 2 more things to remind you of. If the line PQ is parallel to VW, let's just go back and see why this is not happening. There we go. In parallel to VW, if 2 lines are parallel, then I can say the gradient of PQ must equal the gradient of VW. And if they're perpendicular, the relationship is different. If those are perpendicular, if PQ is perpendicular to VW, then the gradient of PQ multiplied by the gradient of VW will always give you -1. Okay, so if a gradient multiplies out, 2 gradients multiplies out to give you -1, it means the lines are perpendicular. The reverse of that, if the lines are indeed perpendicular, then their gradients have a product of -1. Okay, now folks, remember perpendicular means 90 degrees. Okay, let's have a look at our first question. Our first question says the following. We need to prove that a particular triangle, of which they gave me the vertices, I'll put it on for you now, is indeed a right-angled triangle. So let's quickly draw a triangle up here, and then we will work with it and its coordinates. I'm drawing it like this because I don't want to let it be 90 degrees. I don't want you to think it's 90 degrees the way I'm going to draw it. So I'm drawing one that almost looks equilateral, but remember it's not. Okay, and let's fill in the details. They give me the one vertex is K. Let's make that the top one. K is the vertex 4, 4. That's the one vertex. The second vertex they give us is the vertex L. If we put it down here, they say that's 5 and 1. And the third vertex is -6 and 2. So that is a triangle. Deliberately, folks, I did this deliberately. I didn't put it on the XY coordinate system. The fact of the matter is you don't have to. Okay, you don't have to. Let's quickly, always, the first thing you do, check, are there Y coordinates that are the same? Those two are not the same, they're different. These two Y coordinates are not the same, those two Y coordinates are not the same. So we know there's no horizontal line here. And the same for the X values. There's a 4, there's a 5, there's a -6. There's no vertical lines in my triangle. Okay, not that you needed it, but it's always a very good thing to start off with, to see, do I have vertical sides or do I have horizontal sides? Now the question is, prove that one of those vertices is indeed a right angle. In other words, that two of those sides lie 90 degrees to one another. Okay, so there's more than one way I can do it. If you think about it, you can use Pythagoras. Pythagoras works in right-angled triangles, so if you have the hypotenuse squared is equal to the right-angled sides squared and added to one another. That's the one way we can go. So we can apply our distance formula here and look for a relationship. Let's do that, and then afterwards we'll look at a second method. Let's look at KL first of all. Now remember your distance formula. KL is the square root of. Now remember what it said. The y value of k minus the y value at L. So it will be 4 minus 1, and I need to square it. And the same for the x values. Now be careful here. In this particular formula, the order does not matter because I'm squaring it. Okay. If I was working with a gradient, folks, I will have to keep my direction the same. So in other words, if I was finding the gradient of KL, and I start with point K in the y values, I must start with K in the x values. I can't swap direction. Okay, let's complete this. Plus then the distance between the two x's. Now, well, that's a 4, this is a 5. If I take 4 and I minus 5 from it and I square my answer, I get 3 squared, which is 9, plus minus 1 squared, which is 1. So I get an answer here of a square root of 9 plus 1, and that gives me, let me put it down here, the square root of 10. Look again. 4 minus 1 is 3. 3 squared is 9. 4 minus 5 is minus 1, and if I square that, it's a positive 1, so it gives me 10. So I can bank that so long. Now let's go and work out the coordinate or the distance of km. If I work out km, according to the distance formula, it's the changes in the y's squared plus the changes in the x's squared. So if I start with x this time around, for km, I've got 4 minus 6. Now there you've got to be careful. You're talking 4 minus 6. There's a double negative. So that becomes 4 plus 6, which I'm supposed to square. And then to that, I add 4 minus 2, all squared. Okay, now if we quickly do the mental arithmetic there, that is 10 squared, which is 100. This is the square root of 4 plus 6 is 10. If I square that, I get 100. Plus 4 minus 2, which is 2. And if I square that, I get 4. Okay, so there I have the square root of 104. Okay, folks, now for the length of the line LM. Now L has a coordinate of 5 and minus 1. Sorry guys, this is a minus 1 there. It's not a positive one. let's just fix this one up at the top. Gives me 4 plus 1, which will then give me 5 squared. And that changes this answer at the back here. This was a -1 and not a +1. So that gives me, this was my first catch, 4 minus -1, which was 5. 5 squared is 25 plus 1. On that side, the distance between the x values was 4 and 5, and that gives me the square root of 26. Okay, now for LM. The line segment LM has the same thing happening. With the distance formula, it gives me the distance between the x values and the y values. Now be careful. 2 minus -1 is 2 plus 1. Okay, so I get 2 plus 1 that I need to square, the distance between the y values. Then the x values, -6, be careful. -6 minus 5 is -11. Okay, -6 minus 5. I add -6 minus 5, I square that, and I get -11 that I need to square. Okay, so this gives me 2 plus 1, which is 3. It leaves me the square root of 3, the square of 3 is 9, plus the square of 11 gives me, over here, 122. Okay, folks, now what do I get if I add those two together? 9 plus 122 is the square root of 131. Now I need to start looking for relationships there. Which one gives me a right angle relationship, and which, if I add them together, gets me to the result that I'm looking for. Okay, because that's going to confirm Pythagoras' theorem. Now, while you're looking at that, let's look at the second method. Our alternative here will be to look at my gradients. I just learned from the previous slide that if my lines are perpendicular, let's go there. If my lines are perpendicular, the product of the gradient is going to be -1. So let's move back here. If I work out my gradient of KL, my gradient of KL is my change in y over my change in x. So I get 4 minus 1 over 4 minus 5. Now, folks, at the top that leaves me with a 3, and at the bottom that leaves me with a -1, which gives me a -3 as a gradient for KL. If I look at the gradient of KM, the same thing is happening there. For the gradient of Km, which is that line, I need 4 minus 2 divided by 4 minus -6. Now that gives me 4 plus 6. Okay, and that leaves me with a beautiful 2 over 10, which gives me 1 over 5. Now, if you take a closer look at these two gradients, that product is not going to give me -1. So if I calculate my third gradient, I should get either a gradient of a third or a gradient of -5, if indeed there is a right angle in that triangle. Okay, I'm going to say it again. If I now have my third gradient here, which is LM, it must be either 1/3 or it should be -5. If that's the case, I do have a right angle. Now, I hope you guys looked at that. So far, the picture doesn't look good, because if I take 104 and I add 26 to it, I get 130, which is not 131. Now, either way, if I take 131 and I take this 104 away from it, I do not get 26, I get 27. So it doesn't look like this is a right angle triangle. Let's confirm it with the calculation of my gradient. The gradient of LM is indeed then the change in y, which is 2 minus -1. Remember, 2 minus -1. To let you see this. Be careful of that happening It happens so often in analytical geometry, folks, that there's a double negative. You've got to watch out for that double negative because it turns everything else positive. Divided by -6 over, now remember what I said earlier, I must keep my direction the same if I calculate the gradient. I started with m. I said 2 minus minus 1. So I must start with m again. I get -6 minus the y value at L, which is 5, and that gives me 3 over -11, which is not the desired positive 3 I was looking for, or the -5 that I had with Km. So what type of triangle am I working with? Definitely not right angled. Definitely not, because as we saw, Pythagoras doesn't apply, number one. And number two, the gradients don't confirm that there are perpendicular lines. So there's no perpendicular lines. Each line has a different length. So it's definitely not isosceles or equilateral. It is what we call a scalene triangle. Every single side has a different length. Okay, so did we answer the question? Yes, it's definitely not a right-angled triangle, and it's definitely not a regular figure. It's a scalene triangle. Our gradients confirm that there's no right angles, and as well as my look into Pythagoras' theorem, which did not prove that the square of the one side plus the square of the other side gives me the square of the third side. Okay, Ty, any news on that side?
So far, we've got a couple inquiries. I think, let me find one here because I had one earlier. Just wanted to know, will it make a difference with the gradient formula if I just started with the difference in x and then divided it with the difference in y?
Excellent. That's a brilliant question, folks. Your gradient does not work that way around. Your gradient, and it's because of your x variables being the independent variable. Okay, so you've got your vertical distance, your change in y over your change in x. You cannot swap it around. A gradient is definitely not the change in x over the change in y. The change in y always at the top divided by the change in x at the bottom.
Okay, and that was from Lucinda. So, just want to say thank you to her for tuning in. So, on that note, actually just want to make sure that mindsetters, you keep on the page. Keep chatting. Be like Asha, I see you, Lucinda, Cabello, Priska, all those guys who are on the page. Make sure you keep chatting so you can win these awesome prizes, because this is always handy. Everyone always needs a calculator. And the labeler, like, come on, I know I need to label my pencils, my pencil case, blah. So make sure you guys get on the page and get posting. But for me, I'm going to see you after this break. Welcome back, Mindsetters. I hope you had a nice little break. You did whatever you had to do, like I always tell you to do. You went and got water, or you got a snack. But make sure you guys do not go anywhere, and make sure you have your pens and pads and you're paying attention. That's the most important part. Pay attention to retention in the brain for mental stuffs. See, but that's why I keep quiet and hand over to Jacques, who's going to continue with the rest of the session. Take it away, Jacques.
Thanks a lot, Ty. Folks, let's look at our next example that I've got on the board. It says you must find the values of P and Q if, small p and small q, by the way, if point P, which is the point -3 and 2, is the midpoint of the line segment A and B. Now, always in analytical geometry, draw a diagram. Make a little sketch of what we've told you and put all this information off on the diagram. Transfer it. Let's see. There's the point A. A is the point P and Q, they tell me. Then they tell me that P is the midpoint. Now, that's the point -3 and 2. And the relationship there is it's the midpoint. And there's point B, which is the point -1 and 5. Now be careful again, there's a negative. When you have a negative coordinate, be wide awake, because you are going to stumble over that double negative, folks. I've seen it happen so often. Okay, what did they tell me? They told me P is the midpoint of the line segment. So the relationship is, if I add the two extreme points and I halve the answer, I get the coordinates for P. Okay, remember your midpoint formula. Now they're asking me for small p and small q, so I can start off by saying the x-coordinate of point P is indeed the x-coordinate of A plus the x-coordinate of B, which is halved. Now the x-coordinate for P is -3. So I get -3, which is equal to the x-coordinate of A, and that's the P that I'm looking for, plus the x of point B. Now there's the negative coming in, so that is a -1. And that answer is halved. Now folks, that's the fraction. Don't like fractions in math, so let's get rid of it. Let's take the 2 and let's multiply it to the other side. Remember, I can do it because I'm working with an equation here. So the 2 comes to this side, I get -6, which is equal to P -1, and therefore P will be -5. Okay, so I've got the value of P. And remember, the condition was the midpoint is given. So the same thing is going to apply for the y values. The y of P is the y of A plus the y of B, which is halved. Now the y coordinate of point P is 2. 2 is therefore equal to Q plus 5 divided by the 2 at the bottom, and the procedure is exactly the same. Get rid of the fraction by multiplying both sides with 2. You get 4 is equal to Q plus 5. Gooi the 5 over, therefore Q is going to be -1. Folks, there's various ways that they can ask this question. They can give you 3 points, like they did here. They gave us P, A, and B. And now they can say to you that, you know what? The line AP is perpendicular to the line PB. Find the relationship between P and Q. Or they can put a P here and a 6 there and a Q there and a number there and do exactly the same thing. So be aware of what we spoke about earlier. When lines are parallel, their gradients are equal. When lines are perpendicular, their gradients multiply to a product of -1. And in this particular one, they've given me the midpoint. We've got another one that uses the distance formula. They say the following. The length of a line segment, now first of all they give me the line segment, there we go. The line segment is PQ. So if this is point P, remember it's not necessary to make it 100% accurate. As long as you always check. When is it necessary to have an accurate diagram? If lines are vertical or if they're horizontal, then it's necessary to check. Now they tell me something about that line. They say it has a distance or a length of root 13. Now they want me to find the value of A. Only thing you need to remember is I'm working with the distance of a line, so I need my distance formula. And what comes after that is quite interesting. So let us apply my distance formula. PQ is root 13. That they gave me. That's given from the word go. Okay? Now look at what I'm going to do next. I have got a square root on the one side of an equation. So to get rid of it, I can immediately, from the beginning, I can square both sides. Then I don't need to deal with this ugly square root. Okay, then the length of PQ. Let's see. What did we say? It's the difference in the y's that are squared. So if I look at that, it's A minus 4. A minus 4 all squared plus the distance between those x values. Be careful. 1 minus minus 2 is 1 plus 2 all squared. And that is the other side squared, which is 13. Now, folks, always at this point, get the variable to one side and get the numbers to the other side. This is a very easy equation to solve. You do not need to go and square that bracket. Look at what I mean. If I have a minus 4 on the one side, which is what I've got here, on the other side, here I have a plus 9. Why is it plus 9? Because it's 3 squared. So it's plus 9 equals 13. Now look at the poetry here. The 9 is going to jump over the equal sign. It's going to become 13 minus 9. So I will end up on both sides of this equation, I will have a squared number. And even if there wasn't a squared number, if that was 7, it's easier to say the root of 7 when I square root both sides. Okay, let's clean it up. Let's find the value of a. So what was an analytical problem turned into an algebra one. If I take the square root both sides, I get a minus 4. Now be careful. If I take the square root of 4, it can be plus or minus 2. Why? Because negative 2 gives me 4, and so does positive 2. And it's one step from the answer. A is equal to positive 4 plus or minus 2. Finally gives me A is 6, or the value of A is indeed 2. Okay, did we answer the question? Well, they asked us for the values of A, for which that line segment will have a length of 13. Okay, so it's not that bad, folks. As long as you know your formulas, you can do magic with your analytical geometry. Let's move to another example. My next example involves 3 points. I must choose one here, folks, because James tells me time's running out on me. So let me choose the one that works with gradients. They give me 3 points. They tell me point A is the point minus 2 and 4. Point B is indeed a point 2 and 7. And then point C is the point 4 and Y. Now they give me some extra information. They tell me that besides having the coordinates, I know that AB is perpendicular to AC. Now, folks, please, if you look at that, it should tell you a story. If you were to draw this diagram now, can you see that point A is shared? So the right angle is going to lie at point A, most probably. Not most probably, most definitely. AB perpendicular to AC. Do I need to know that? Do I need to draw it? I don't think in this case it's necessary. As long as you remember, because this was given, you can say that the gradient of the line segment AB multiplied by the gradient of the line segment AC has to be minus 1. If lines are perpendicular, the product of their gradients will be negative 1. If they go beyond that and they ask you, okay, where's the right angle? There's no need for you to go and work out all three the gradients and then decide. By that I mean find the gradient of AB and then BC and then AC and see what the relationship is. You can see which vertex has been shared. And that's most probably where your gradient is going to be perpendicular. Your right angle will lie there. Okay, let's see the gradient of AB. If I want the gradient of AB, be careful of negatives. So it's 7 minus 4 at the top over 2 minus minus 2. Remember I told you that double negative. So it's 2 plus 2. That multiplied by the gradient of AC. Now, if I look at the y values, I get y minus 4 at the top divided by that x value minus this x value. And there it is again, the double negative. 4 minus minus 2 gives you 4 plus 2. That product has to be minus 1. Now remember, these are two numbers. This is a rational number, that's a rational number. I need to find the value of y. Okay, I get 7 minus 4, which is 3, and 3 over 2 plus 2 gives me 3 over 4. So here I'm stuck with 3 over 4 that I multiply with y minus 4 over 4 plus 2. That gives me 6, and that answer needs to be minus 1. Okay, now you guys can remember how to multiply fractions. I multiply a fraction by multiplying the numerators and dividing it by the product of the denominators. So at the top, I'll get 3 times y minus 4. And at the bottom, you'll notice I'm not multiplying it in because I'm going to solve for y. At the bottom, I get a beautiful 24, and that is still equal to minus 1. So now it's over to algebra again. Okay? If I multiply the 24 across, I get 3 times y minus 4. And notice I'm still not multiplying it in. That gives me minus 24, and now I can divide the 3 away. I get y minus 4, which is minus 8, and all that's left now is to kick the 4 over, and I get that y is indeed minus 4. All of this is algebra, folks. That's algebra. But you had to interpret the condition analytically. And the condition was there's 3 points given. The relationship was the 2 line segments that joins them are perpendicular. Use that to find the unknown value, which was y in this case. Okay, folks, I hope that helped you. And I hope that you realize you need to know your conditions and your formulas to do analytical geometry properly. Ty, up to you.
Yes, and on that note, on that awesome note, which all the mindsetters seem to be excited about, they said they just keep saying that they had fun, they've been enjoying the show, because a lot of them were saying that, you know what, it's like I get to go home, and I can still continue my lessons from school.
Yeah.
So it's just like, well, that's what we're here for. So for me, I'm going to make sure that I peel through the page, so I make sure I find the mindsetter who deserves this the most. But from now, guys, I'm going to see you guys next time. So guys, make sure you tune in tomorrow even for the other lessons for grade 10s. So to make sure you do not disappear. But from us, we're going to see you next time.
Cheers.